Bismillah ar-Rahman ar-Rahim. Today our lecture will be about the design of control systems in time domain using the root locus technique. This is chapter 5 from my handouts, and as we have previously discussed in the second page of chapter 1, the second page of chapter 1, which is at the top of that page, we have described or mentioned that the goal of control systems is to modify the plan such that the output or the response is following the input signal or the desired input, the reference signal according to certain performance specifications. And here we are repeating this fact that control systems are designed to perform certain tasks, and those tasks, they are given in as a performance specifications, okay, in time domain. And those specifications, they are divided into two categories. The first one is the transient response requirements, and generally we describe them directly in terms of maximum overshoot MP and settling time TS due to step input. This is the directly, okay, in terms of the response, or we describe them in terms of omega n and zeta, omega n and zeta. This is the transient response specifications. And the second part is the steady state requirement. That is related to the steady state error that we have previously, due to step input, that we have previously covered in the previous chapters. And those performance specifications, they don't yield one optimal solution, and they might result with more than one solution, one design for the controller. And this is very important fact, that they should reflect the priorities of the designer for the control system, depending on the application where we applying the control system in certain plants. So when we design the control system in time domain based on root locus technique, there are two main assumptions, two main facts that this design process is based on. The first one is that reshaping of the root locus of the system or of the original plant, that assume that we have an existing plant and the response of that system or that plant is not satisfying our requirements that were given in step 1 and step 2 above. And then we should reshape the root locus of the old system or of the existing plant by the addition of poles and zeros to the loop transfer function of the original system. And when we add poles and zeros to the original plant or the original system, then we should, in this process, we are forcing the root locus, the new root locus, after the addition of poles and zeros, to pass through certain desired closed loop poles that will be specified based on this maximum overshoot and the settling time. That will be specified based on maximum overshoot and the settling time. So this is the first fact that the design process and root locus is based on. And the second fact is the assumption that in the new closed loop system, after the addition of the poles and zeros or the addition of the controller, we have a pair of dominant closed loop poles. We have a pair of dominant closed loop poles that were described or specified according to certain damping ratio, and which is zeta or delta, and undamped natural frequency, which is omega n. So in order to clarify what's meant by dominant closed loop poles, let us have this empty page and assume that we have a system, and we will locate, or we will specify the closed loop roots, the closed loop poles of the system, or the roots of the characteristic equation in this S-plane. Okay, so this is the imaginary axis and this is the real axis, and we will assume that the system is stable. This means that all of the roots, they are in the left half side of the S-plane. Assume that we have a pair of complex conjugate poles here around like -1. This is the real part. The real part, alpha is equal to -1. Assume that alpha is equal to -1, which is the real part of those pair of complex conjugate roots. So its real part is -1. So if, in order to satisfy the dominance of those closed loop poles, then the remaining poles of the transfer function, or the roots of the characteristic equation, should be far away. The remaining poles should be far away from those dominant closed loop poles. So we have two categories of poles. Those are the dominant, and those are the far away, which are non-dominant. So we have dominant closed loop poles here, and we have non-dominant closed loop poles. In order for those poles to be dominant with respect to the rest of poles which are non-dominant, then the real part of the dominant, assuming in this example it's -1. Okay, those non-dominant closed loop poles, they should be at least 4 to 5 times the real part larger than the dominant the real part of the dominant closed loop poles. So this means that, like, assuming this is the closest one to the j omega axis of the non-dominant group, then this should be at least -4 or -5 or to the left. If this ratio between the real part of the dominant over the real part of the non-dominant, and when we speak about the non-dominant, we select the closest to the right, and if this closest to the right is satisfied, then the others which are to the left of this one is also will be satisfy the condition. So the real part of the dominant closed loop poles, as compared to the ratio between the real part of the dominant with respect to the real part of the most dominant, or the right hand side of the non-dominant group, should be at least greater than or equal to 4. If this ratio is satisfied, this means that these are dominant closed loop poles and these are non-dominant closed loop poles. But assume another scenario. For closed loop poles, and assume that this is -1, this is -2, this is -3, and this is -4, and assume that we have one here and one here. So the real part, I am assuming that the real part of those pair of closed loop poles, it's equal to -1, and assume that there is another pair of closed loop poles that is located here. So if we pay attention to the real part of those pair, it's around -2. So the ratio between -2 over -1, it's less than 4. So this means that these are not dominant closed loop poles, because those closed loop poles, they are close to them. So the distance, the relative distance of the dominant closed loop pole to the non-dominant, as I previously mentioned, it should be at least 4 times. So in order for those to be non-dominant, at least they should be placed here around the -4, around the -4, -1, -4, this means -4 over -1, which is equal to 4. So in this way, this is non-dominant and this is dominant. But if the roots, we consider those roots, so this is not those pair here at about -1, they are not dominant, because those pair of complex conjugate poles, they are close to them and the ratio is less than 4. I wish that by this clarification we have understood what's meant by dominant and non-dominant closed loop poles. So we return to our discussion that we have two assumptions. We have two assumptions, or the design process based on root locus. It's based on two things. Number one, it's the reshaping process. It's the reshaping process of the root locus by adding poles and zeros in order to force the old root locus to pass through the desired closed loop poles. And the second thing is the assumption that after the addition of the controller, the pair of dominant closed loop poles that we have specified based on omega n and zeta, they are really dominant and they satisfy this ratio not less than 4 as compared with the other non-dominant poles. So what are the design steps of controllers in root locus? In the design process of any controller, whether using root locus or body plot or PID controllers, we should start with the simplest design scenario, and then if we achieve our goals, then there is no need to go to a more complex design process. So if we achieve our goals, then we should stop, and there is no need for complexity if simple design can achieve our goal. So in our case, we have two scenarios for the design of controller. The first step and the first procedure is the gain adjustment. And if gain adjustment does not work, then we should add a controller as given in the compensation step. And in order to understand this fact, I will clarify it using the following pages. Assume that I will assume a certain root locus, okay, a certain control system plant with 3 poles, and based on our previous chapter discussion, we can roughly draw the root locus of such system, and the root locus of such system will be approximately like this, and one like this. So there will be 3 branches, one with plus 60, one branch or the asymptote will be minus 60, and the third one will be minus 180 degrees. So these are the 3 branches of the root locus. Okay, now I will assume a certain desired location for the closed loop poles. In the first scenario, I will assume that the desired closed loop pole lie on the root locus. In the first scenario, I will assume that the desired closed loop pole lie on the root locus. So this is SD1, and this is its complex conjugate SD2. And in this scenario, I am assuming that the desired location lies on the root locus. If it lies on the root locus, then as we have previously covered in our previous chapter, this means that the angle condition is satisfied. Since all the points on the root locus, they satisfy the angle condition. And our design process will be only to apply the magnitude condition in order to find what value of K make this as one of those two pair of roots as our desired location. So we can apply the magnitude condition K, which is equal to minus D over N, and in case of the magnitude we assume K is equal to D over N as a magnitude. There is no need for the minus, we take the absolute value, and based on this step we calculate the magnitude K. In order to be more specific, okay, K will be the application of the magnitude location at this desired location. So will be magnitude of D over N of the original plant without any addition of the controller at SD, at the desired location. So we can satisfy, we can find this K, and its value will be from 0 to infinity, okay, within our range because it lies on the root locus. And once we find this K, then our design process is over, and this is what we mean with the gain adjustment. So the gain adjustment is used when the angle condition, the odd multiples of 180 is satisfied, or the desired location of the closed loop poles that we have already, we need our system to pass through, already lies on the root locus. This means that there is no need to add poles and zeros, there is no reshaping process, and only we apply the magnitude condition K at the desired location for the old system, and our design process is over. So this is regarding the gain adjustment. This is what I mean by gain adjustment. And if we will cover another approach, which is the compensation. I will assume the same system, and we have 3 branches, 1, 2, and this is the third. And in this scenario, I will assume that the desired location, this is SD, is not lying on the root locus, So in this case, gain adjustment will not solve our design problem, because at SD, the root locus is not passing, and at SD, the value of the angle condition is not odd multiples of 180. And in this case, we should add poles and zeros to the loop transfer function or the original plant or the original system in order to reshape or bend the root locus, the old and new root locus, such that the new root locus should pass through the desired location. And this is what I mean, that we should reshape means bending the root locus after the addition of poles and zeros from the controller. This is what I mean by compensation. And this new root locus, after the addition of poles and zeros, it should pass through the desired location. So it should be passing through the desired location, and in this way a compensator or a controller is required, and this compensator will provide the system with the deficiency in angle, because at SD the angles of poles and zeros of the original system, at SD it's not odd multiples of 180, so there is a slight change, or there is a difference. Like assume that there is a difference of 30 degrees. The angle at SD is 150. So there is a difference of 30 degrees. And those 30 degrees, they will be provided from the compensator or the controller. And this compensator or controller will provide those 30 degrees. And if the controller or the compensator provide those 30 degrees, then this means that the new root locus should be passing through the desired closed loop pole location that we have already specified based on omega n and delta. Okay, this is in indirect way, or based on MP, the overshoot, and the settling time if it is from the performance specification from the plant. So this is what we mean by gain adjustment and compensation, and I wish that after this discussion everything is clear to all of you. So let me again clarify. Gain adjustment: if the desired closed loop pole lie on the original root locus of the original system, then gain adjustment will meet the specification, and by this gain adjustment we will increase the gain value, and when we increase the gain value we will be approaching the imaginary axis, and this will make the system less relative, the relative stability will be reduced, and it will improve the steady state behavior of the system, because as Kp or Kv or Ka increase, by increasing the gain, the Kp or Kv or Ka will increase, and if they are increased then the steady state error will be decreased, as we discussed previously in the previous chapters. But the penalty for this process, the price for this process is that the relative stability will be deteriorated or will be reduced. So regarding the compensation, this is used if the desired closed loop poles does not lie on the root locus, and then we should add a compensator, and this compensator will add phase such that it will reshape the root locus, the old root locus, and the new root locus will pass through the desired pole, and this process is called compensation, and the device itself is called compensator or controller, and controller or compensator compensate for the angle deficiency of the original system. So let us jump to the next point. In designing the control systems by root locus, okay, or even by frequency domain, the final design of the controller is not unique. This means that the optimal solution may not be precisely defined, and we might have more than one design for the controller based on the design specifications. And the second point is that the plant dynamics is fixed and we cannot change. The IR, they cannot be modified and they are unalterable. This means that if the desired specifications are not met and the gain adjustment does not solve the problem, then we should add a controller, and we should not change any of the dynamics of the original plant. And as we know previously that we should add a controller. This is GC before the existing plant GP. So we should not change anything in the plant, and if we have any desire or will, we should add or introduce this controller, and by introducing this controller, the new G new will be GC GP, okay, will be GC GP, and based on that we are equivalently, this is G, we are equivalently changing the overall forward path transfer function without exactly changing the plant transfer function, but using the controller, because any change of the controller will change the overall new forward path transfer function. And this is what we mean by that we should not change the plant, and if we have anything to do, then we should do by the introduction or through the introduction of the controller. And regarding the next point, the original plant dynamics, if we add a controller, whether in gain adjustment or compensation, it might be the original system might be unstable for all values of gain, or stable but not matching the desired specification. And in this case, we should proceed in the design of steps of the controller as we mentioned previously, according to the gain adjustment in the first scenario, and then if we fail in the gain adjustment, then we should go to the compensation. And compensation, it can be viewed as a design of a filter or a transfer function whose characteristics tend to compensate for the undesirable or unalterable characteristics of the plant. And in root locus, the design problem will be the determination of the location of the poles and zeros of the compensator. We should add a pole and zero, and we should specify their location. It's not random, it's on the design, using the design procedure, and those specific location of the poles and zeros, they will reshape the root locus, the old root locus, such that a pair of dominant closed loop poles can be placed on the new root locus. Okay, I wish till this point everything is clear regarding the general concepts of designing the controllers. Okay, now we will switch to the next point regarding the asymptotes information, that we discussed in the previous chapter. And if you remember, we have discussed that regarding the asymptotes that the root locus, the infinite branch of the root locus will be in their direction as s approaches infinity. Regarding those asymptotes, they have two pieces of information that fully describe them. Number one is their intersection with the real axis in the s-plane sigma a, and the other one was their angles phi a. And if we focus on this phi a, when n minus m was 1, okay, the possible phi a's was 180 degrees, if you remember. And when it was 2, it was 90 minus 90. And if it was 3, it was, if you remember, 60 minus 60 and 180 degrees. All of these we have discussed previously, but just a reminder for you, because I think the memory might be a little bit volatile and you have lost such information. So and we continue in this process. So for this case, this is the asymptote. It will be minus 180 degrees. And if we increase the number of branches, it will be to 2, will be 90 and minus 90. And if we increase it to 3, it will be 60 minus 60 and 180 degrees. So from here, it's obvious that as we increase the value of n minus m, then the angle phi a, the first angle, will be reduced. Here it was 180, the first angle. The second angle, 90 in the second case. In the third case, it was 60. In the fourth case, it will be 45, and so on. So if we keep increasing the n minus m value, which is the number of asymptotes, as the number of asymptotes increase, okay, this means that the root locus will be directed to the right hand side of the s-plane, or toward the j omega axis with smaller angles, and it will be unstable using smaller values of k. This we have already previously covered, but just as a reminder. So as the number of asymptotes increase, okay, this means that the asymptotes, some of the asymptotes will be directed to the right hand side, and this shifting to the right hand side, this means that the root locus is directed also to the right hand side, and there must be a value of k. If n minus m is greater than or equal to 3, there must be a value of k beyond which the system will be unstable and it will be crossing the j omega axis and moving to the right hand side of the S-plane. And this is what I need you to remember from the previous chapter. Okay, now this is what I have covered. We have phi a, which is 180 divided by n minus m, and we will discuss the effect of adding zeros and poles based on this phi a. Okay, so assuming that we have constant m. Constant m, I will remind you that m is the number of zeros and n is the number of poles. N is the number of poles and m is the number of zeros. So if we use constant m, this means the number of zeros is constant, and we add more poles. Addition of more poles, n increase, this means that we are adding more poles. Okay, then what will happen? N minus m in the denominator will be increasing. As a result, phi a will be decreasing, and this fact, as I have previously mentioned in the empty page previously, just before a few minutes, then the root locus will be bending to the right hand side and the system will become unstable. While on the other side, if we assume that n is constant, which is the number of poles, and we increase the number of zeros, then n minus m, if we increase the number of zeros while the number of poles is constant, n minus m will be reduced, and this means that phi a will be increasing, and if it is increasing, this means that the root locus will be bending to the left hand side, and this means that it has a better relative stability, or it's moving away from the j omega axis. So to conclude, this is if the addition of poles, it bends the root locus to the right hand side, while the addition of zeros, it bends to the root locus to the left hand side. This is a step which is not okay, because it will spoil the stability, and as we will see later, and this step, since it will bend the root locus to the left, this is a very nice step. So we will reach to the conclusion that addition of zeros is good. It will bend or shift the root locus to the left, or reshape the root locus to the left, while the addition of poles, it has a negative impact. It will shift or bend the root locus to the right hand side. And now we will cover those two factors in details. We will cover them in details. So in the next section we will cover the effect of addition of poles to the loop transfer function using the controller. This addition of poles or zeros will be using the controller. As we have previously mentioned, we cannot modify or change the plant. Anything that you need to change and show your experience and your knowledge by incorporating the controller instead of modifying the plant. So as we have mentioned, the addition of poles, it will pull or shift the root locus to the right, and this shifting to the right, it will lower the system relative stability, and it will slow down the system response. So as I have mentioned, if we add pole to the loop transfer function, then the number of asymptotes will be increase, n minus m will increase, and this increase will pull the root locus to the right hand side, as we previously mentioned. And regarding the sigma a, which is intersection of the asymptotes with the real axis, it cannot be specified. Why? Because here we are changing in both the numerator and denominator. The denominator we are changing because n minus m is increasing, and we are adding poles, and then the summation of all real part of poles is changing. So there is a simultaneous change in the numerator and denominator of this equation, and since numerator and denominator are changing simultaneously, then we cannot specify whether sigma a will be shifted to right or sigma a will be shifted to left. Okay. Regarding the third point and the fourth point, I will cover it using few pages that I have prepared yesterday in order to clarify things for you. So, assuming that we will, as I have mentioned, we will discuss the effect of adding a pole on zeta and omega n. So assume that we have an original system that has two poles and it has a transfer function as given this. It has like one pole at -1 and the other pole at -7. And if we draw its root locus, this is the red one, this root locus will be the root locus of the old plant or the original system. And this original system, we have added a pole to it at s is equal to -5 as shown here. And the transfer function will become the new transfer function after the addition of this pole. And the root locus will be the blue one. This is the root locus, will be the blue one. As I have mentioned here, we have n for the old, we have n minus m2 and 90 minus 90 degrees. This is minus 90 and this is 90. While after the addition of pole, the angles became 60, minus 60 and minus 180. And this is what we mean that the root locus after the addition, it has bended to the right hand side. And this means that the relative stability is deteriorated. So, using a detailed graph, we will see the effect. Using a detailed graph, we will see the effect using this graph. We will see okay. So as I have previously mentioned, this is the old root locus. This is the new root locus after the addition of pole. So if we assume that we have constant omega n. Constant omega n, as I have previously mentioned in the previous chapter, it's a circle. It's a circle with certain radius. This is the circle with certain radius of omega n is equal to 5. And the intersection of this circle with the old root locus and the new root locus, it will give us the old value of zeta and the new value of zeta. It will give us the old value of zeta and the new value of zeta. And in this regard, so this is as I have mentioned, the constant omega n loci, and this is the intersection of this constant, which is a circle. This is the intersection of the constant omega n loci with the old root locus, and it will give us constant zeta, which is equal to 0.78, and the intersection of this also loci, this circle, with the new root locus, it will give us the new value of zeta, which is 0.17. So we are assuming that this is for omega n constant, and we are checking the effect of addition of a pole on the zeta values. So this is the old value and this is the new value. And since the new value of zeta is less than the old, this means that the relative stability of the new root locus or of the new control system is less than the relative stability of the old, because as we move to the right hand side, then the relative stability is deteriorated or it's affected negatively. So this is what we mean, that for constant omega n loci, zeta nu will be reduced, and based on that, if zeta is reduced, the overshoot of the system will be increasing. As you remember, there was formulas for MP you have taken in modeling and simulation course, and this relative percentage overshoot will be increasing for the new system, because as zeta decrease, the MP will decrease, and the overshoot of the old system will be less than the overshoot of the new system. And this is the major drawback, that the relative stability of the new system will be less than the relative stability of the old system, because the overshoot has increased, and also the new location is closer to the roots, is closer to the j omega axis than the old values of the roots. Now let us switch to the next fact about if we assume that we have a constant zeta loci, and constant zeta loci is drawn as beams with certain angle. We have previously also covered its beams with certain angles, and here we have, as I mentioned, this is the old root locus, this is the new root locus, and we will check the intersection of this beam. This is the beam, one of the beams, and this is the other beam. Okay, so based on that, this intersection point is the intersection of this beam with the new root locus, and this point is the intersection of the beam with the old root locus. So this is omega n here, it's omega n old, and here it's omega n new. Okay, because omega n is the radial distance between origin and the desired location. Okay, because it's circle, as I have mentioned. So here we notice that omega n new is less than omega n old. And if you remember, all of the time related parameters, Ts, T peak time, and T settling time, peak time, and settling time, they are inversely proportional to the omega n. This means that as omega n increases, the time related parameter will be reduced, and if the time related parameters will be reduced, this means that we have faster response. While if omega n is reduced, this means that, so this is omega n, as I mentioned, this is omega n new, which is 3.5, and this is omega n old, which is 7.75, and omega n new is less than omega n old. And since all time related parameters, they are inversely proportional, this means that the time of this new system will be larger than the time required for the old system, or the time of the old system is smaller than the time of the new system. And if the time of, as I mentioned, if the time of this new system is larger, this means that the system becomes slower, and if it's becomes slower, this is what we claim in the comments that we have mentioned. This is what we claim on the comments that we have mentioned, and in this manner, we will go back to our previous slides. So this is what I have mentioned regarding for particular value of zeta. I have this is the two figures that we have discussed, that regarding the system finally will become slower. Okay, the system after the addition of a pole will become slower because all omega n is reduced and all time related parameters have increased, and for particular value of omega n here this fact lowers the system relative stability and increase the overshoot of the system. And this figure show a system of one pole, two poles, three poles, in order to see that as we increase the number of poles, the system will be moving or bending to the right hand side of the S-plane, which is the same fact that we have mentioned in this point. In this point, that addition of poles will bend the root locus to the right hand side, and this fact will lower the system relative stability and will slow down the settling of the system. And in this way we have completely covered this part, and in the next lecture we will see the effect of addition of zeros to the loop transfer function. Thank you, and see you in the next lecture inshallah.